Hi guys, welcome to this set of videos. These videos are going to follow along with chapter 4 out of your guys' textbook. We're going to start off here now with section 1, where we're going to begin to look at what's known as quadratic functions. Now, here in chapter 4, we're going to do just about everything you can do with a quadratic function. We're going to look at graphing them. We're going to look at factoring them. We'll be solving them. Lots and lots of things having to do with quadratic functions. But to get us started here in section 1, what we want to do is these two objectives are learning targets, things you should be able to do by the time we get to the end of this set of notes. And the first one's going to be this. Should be able to just in general graph a quadratic function. So if I give you a quadratic function, which I will, how are you going to go about graphing it? We'll give you some details on how to do that. And then after we get done doing that, a number of other things that we're going to ask you to be able to find after you get done graphing. We're going to ask you to be able to find intercepts, maximum and minimum values for the quadratic function. And these maximum and minimum values are generally going to be where the vertex of the parabola is, and we'll talk about all of that as well. So let's go ahead and jump right into these notes and get started here in chapter 4 with quadratic functions. Let me slide this up and give you an example of a quadratic function. You will become very, very familiar with this equation by the time we get to the end of this chapter. And it's this one right here. Let me highlight it for you. F of x is equal to ax squared plus bx plus c. That guy right there. Now, when it's a function, right, we'll use our function notation. For example, this one is f of x. It could just as easily be g of x or n of x or k of x or q of x, whatever. It doesn't matter what we name our function, right? It'll just have a name. But the ax squared plus bx plus c. All right, real important. Let me talk about a couple of things here. First, a, b, and c are coefficients, all right? They represent the leading coefficient in each of those terms. These are going to be numbers. They could be positive, they could be negative, they could be rational, irrational. They're, of course, going to be real numbers, all right? They're going to be real numbers, but they could be any real number. There is one stipulation, though, and it is that a cannot be 0, and here's the reason why. This is a quadratic function because of the x squared term. In fact, anytime you see an x squared as the largest power in a function, it's going to be quadratic. So that represents our quadratic term. That's what makes it quadratic. Now, if a were 0, you would then have 0 multiplied by your x squared. Well, 0 times anything is 0, and that whole term would go away. In which case, you would now no longer have a quadratic function, and since chapter 4 is all about quadratic functions, that really kind of defeats the purpose. So, we will never have an example where a is 0. If we did, the x squared term would drop out, and we'd just be left with a linear function, the bx plus c, which is y equals mx plus b. It's just a straight line function when that leading coefficient is a 0 and the x squared term drops out. But we've already done linear functions. We did that in the previous chapters, so a will never be 0. Let me give you a couple of examples of what you can expect to see when it comes to quadratic functions. First, this. When graphing a quadratic function, you'll become very familiar with this term. If you aren't already, let me highlight it for you. All quadratic functions, when they are graphed, will take the shape of what is known as a parabola. It's going to look very similar to a U that you can either open up, that you can open down, right? But it'll look kind of like an elongated U. That's a parabola. We call it a parabola, so please don't call them U's, right? We'll refer to graphs of quadratics as parabolas. And I've given you a couple of examples. Here's one where I have both the quadratic term, the linear term, and the constant, x squared plus 4x minus 3. In this case, let's go ahead and just get some practice doing this. In my first example, what is the value of a? Well, in this case, a would be 1. My b would be what's in front of the x term, so b would be 4. and my c is going to be whatever the constant is tacked on the end. In this case, that'd be a minus 3. Those guys all go with that one. But now I've got another example for you here. I've got this negative x squared plus 1. Well, that one looks a little different, so let's go ahead and run through this and see if we can figure out what's going on here. My a, well, the a is going to be what's ever in front of the x squared term, and it looks like I have a minus 1. So a is minus 1 in this case. B is going to be what's ever in front of just the x to the first power. And I don't have one. So how did that x wind up going away? How do I get rid of that x, right? Well, I get rid of the x if I multiply it by a 0. So what that means is that my b is 0, right? Because 0 times x would be 0. That whole term would drop out. I'm left with just my constant there on the end. C is a positive 1. So all of those guys go with that one right there, and I tell you right here in this quadratic equation, b happens to be equal to 0. I got one last one for you right here. F of x is equal to x squared. Let's go ahead and name all of our constants. A comes first. A is going to be what's in front of the x squared. Well, there's my x squared, and the coefficient in front of it is just a positive 1. B is going to be whatever is in front of my x. And I don't have an x. So again, the only way to get rid of that x would be if I multiplied it by 0. So my b must have been 0. C is going to be the constant tacked on the end, plus or minus c, whatever it is. And I don't have a constant anywhere. That means it must have been 0. So my c is also 0. And I made that little note for you right here. Both b and c are 0 in this case, which is perfectly okay. Remember, it's just a that cannot be 0, just a. Let's jump on over to the next page. We'll learn a few more things about quadratics. This table right here that I've given you is really important. We're going to pull some great stuff out of this. A couple of small formulas that you will need to memorize, and it's this one right here. When graphing a parabola, it is going to be very, very important that you be able to find the axis of symmetry. Now, the axis of symmetry is going to be a line, all right? It is actually going to be a vertical line. Now, we know that all vertical lines have the formula have the equation x equals something, right? Because it's a vertical line. Well, that's exactly what I've got here. I have x equals, and it turns out that the axis of symmetry is going to be negative b divided by 2a. And yes, this b and a are the b and a, or the a and b, that come out of your general equation for a quadratic, the ax squared plus bx plus c. So that b in this little formula and the a in that formula comes straight out of the equation, or the function that I'll give you in the problem, right? So I'll give you a function. You just need to find those leading coefficients, which is why we practiced on the previous page. And once you know the value of a and b, just plug them into the formula, and you'll get your equation for the axis of symmetry. A couple other really important things we'll get some practice with here in a second is this one. The y-intercept is going to be the value of c, right? So we know that a and b, those coefficients, are going to go in to help me find my axis of symmetry. But what about my constant hanging out on the end of my quadratic? Well, it turns out that is going to be the y-intercept. That'll be where the parabola, when I graph it, the parabola will cross the y-axis at that value of c. The rest of this we'll get as we go through an example problem. Again, this is a parabola. You should recognize the shape of it. I'm sure that you saw parabolas at least a little bit in Algebra 1. If you don't recall this from Algebra 1, don't worry. We'll cover everything. But hopefully at least the shape of that looks familiar to you. If not from math class, maybe even from physics. All objects that are projectiles. Any object in projectile motion will actually take the shape of a parabola as it's in its path through the air under just the force of gravity. It'll take a parabolic shape. So anyway, you may have seen it in other places besides math. So again, when we find this axis of symmetry, what it's going to be is a vertical line that will split our parabola right in half. That's why we call it an axis of symmetry, right? Symmetry means that our graph is symmetric around that axis, right? It's mirror images on either side of my axis of symmetry. So let's go ahead and take a look at an example that I've got for you right down here. And we'll show you the way that these are going to go when we start doing them together. What I've done is I have given you a quadratic equation. Real quick, let's go ahead and label what we know. Remember, our general equation is this. It is ax squared. Hang on, sorry, one second. Ax squared plus bx plus c. It might not be a bad idea for you as you're getting used to doing these kinds of problems to just go ahead and write that every single time. Because now what it's going to do is it's going to allow me to quickly identify what are those coefficients. Well, in this equation, this quadratic equation, my a is a 1, my b is a 6, and my c is a -2. Now, what do we do with those? Well, the first thing you're going to need to do is find the axis of symmetry. Remember, from the chart above, we do that by finding x is equal to a -b over 2a. Well, at this point, now that I've identified what b and a are, we just plug that stuff in. So x is going to be equal to a negative. My b is a 6, so 6 over 2 times a, and my a is a 1. All right, well, what does that come out to be? It looks like if I go ahead and do a little bit of algebra here, negative times 6 would be a -6, and a -6 divided by 2 would be a -3. So my axis of symmetry is going to be a vertical line at x equals -3. And that's exactly what I've graphed for you here in this picture, right? My axis of symmetry, x equals -3. And we'll go ahead and make it, at least I will make it a dotted line. That way I don't confuse it with my actual graph, which is the parabola, right? We're trying to graph this function, which should look like a U, a parabola. And technically, my axis of symmetry is not part of that graph. It's just something I'm going to use to help me graph the parabola. So I'll make it a dotted line so that I don't confuse it with the graph I'm actually trying to get. Now, once I've found that axis of symmetry, the next thing you're going to do is go ahead and plot your y-intercept. Well, remember from the table above, we know that the y-intercept is equal to c. Well, we found c, right? We pulled c out of my quadratic already. We know that it's a -2. So my y-intercept is going to be at -2, and remember the point x comma y, so 0, -2, right? Because when you cross the y-axis, x is 0. And so I went ahead and I plotted that point for you, 0, -2. Now, here's what you'll then need to do, right? My y-intercept is at 0, -2. Real quick, think for a second. How far is that from my axis of symmetry? Yeah, it's 3 units. Since my axis of symmetry is at -3, and I've plotted my y-intercept at 0, x equals 0, I'm 3 units, right? I just go -3 units and I'll reach my axis of symmetry. Well, we know that the axis of symmetry splits the parabola down the middle. So how do I get this second point? Just go 3 units past the axis of symmetry. Since this distance right here is 3 units, this distance right here must also be 3 units. If my axis of symmetry is at -3, subtract 3 and you'll plot your point at -6. -6, right? So that's how you get those 2 points. It's symmetric around that axis of symmetry. Once you find the y-intercept, just go the same distance on the other side of the axis of symmetry and you'll have your second point. All right, so there we go. I've found those 2 points. Now what we're going to do is go ahead and graph the parabola. And the way that we do that is we need to find the vertex. Here's how you find the vertex. In order to find the vertex, you're going to plug the x value from your axis of symmetry, this guy right here, the negative b over 2a, which for us in this example problem was a minus 3. But in any problem, you're going to plug that value of x into the original function to get out your y value, right? I'm going to plug in an x to get out a y. It's going to give me an ordered pair that represents my vertex. Let me show you how this works. I'm going to take my function, whatever my function is, I'm going to plug in a negative b over 2a, which I already found, right? I found it over here. It was a negative 3. Now, what is my function? Well, in this example problem, it's an x squared plus 6x minus 2. Okay, so everywhere I have an x, I'll plug in that negative b over 2a, which again, for us, is a minus 3. So let's go ahead and do that. I'm going to do f of minus 3, which means I'm going to have a negative 3 squared plus 6 times a negative 3 minus 2. Let's go ahead and do a little bit of mental math here. A negative 3 squared would be a 9. 6 times a negative 3 would be a minus 18. Subtract 2. Again, that's all equal to f of minus 3. And we wind up getting f, sorry, I got to slide over a little bit because I ran out of space, f of negative 3. Well, minus 18 minus 2 would be a minus 20. You add 9 to that, right? And you should get minus 11. Now remember, what this does is it gives me an ordered pair. In fact, this ordered pair, x, was a negative 3. Y was a minus 11. So I plot that point. I plot negative 3, negative 11 right there. Then all you need to do is just connect your 3 points, right? I connect from my vertex through my y-axis, right? That gets me half of my parabola. Since it's symmetric, on the other side, I'll go from my vertex through that other point I found by going the exact same distance past the axis of symmetry to get the other half of my parabola. Guys, that's the way that we're going to start off by graphing these parabolas. I know it looks like a lot of work. It'll go a lot faster once you get used to it. So head on over to the next page of the notes. We'll practice graphing a few more parabolas, and I'll meet you guys there.